A wide, nearly enclosed basin sits quietly within the Appalachian Mountains, its shape so symmetrical and its boundaries so sharply defined that it raises immediate questions. How does a valley come to be surrounded by higher ground on every side, with only a narrow opening where water escapes? Why does its interior behave like a natural bowl, collecting colder air and delaying seasonal warmth compared to nearby ridges? And perhaps most compelling of all, could such a formation really be the scar of an ancient impact, or the remnant of a long-extinct volcano, preserved across hundreds of millions of years? Burke's Garden, located in the Appalachian region of Virginia, spans roughly 8,000 acres, or about 32 square kilometers, forming an oval depression encircled by mountains that rise to elevations exceeding 3,000 feet, or about 900 meters, while the valley floor itself sits near 2,000 feet, or approximately 600 meters above sea level. From within this basin, the surrounding terrain appears to climb in every direction, creating a visual and physical enclosure that is both striking and unusual within the broader Appalachian landscape. At first observation, the geometry alone invites comparisons to more dramatic geological origins. Impact craters formed by extraterrestrial collisions often display circular outlines and enclosed interiors. Volcanic calderas, created when magma chambers collapse, can also produce basin-like structures surrounded by elevated rims. Yet Burke's Garden does not conform to the diagnostic features expected from either of these processes, and the explanation for its formation lies instead in the slower, more methodical mechanisms of structural deformation and erosion acting over immense spans of time. The Appalachian Mountains themselves began forming over 400 million years ago during a series of tectonic collisions that compressed and folded layers of sedimentary rock. These rocks, originally deposited in ancient seas, included alternating sequences of sandstone, limestone, dolomite, and shale. Each of these materials responds differently to weathering and erosion. Sandstone, composed largely of quartz grains, is relatively resistant and tends to form ridges. Limestone and dolomite, both carbonate rocks, are more susceptible to chemical weathering, particularly dissolution by slightly acidic water. Shale, being fine-grained and less cohesive, erodes even more readily. Within Burke's Garden, this contrast in rock strength becomes central to understanding its shape. The mountains that define the perimeter are composed predominantly of sandstone, forming a durable ring that resists breakdown. Inside that ring, the valley floor is underlain mainly by limestone, with zones of dolomite and shale interspersed. Over time, these softer rocks have been preferentially eroded, lowering the interior relative to the surrounding ridges. However, differential erosion alone does not explain the enclosed geometry. The key structural feature underlying the valley is an anticline, a fold in the rock layers that arches upward. In this case, the anticline is not simply a linear ridge, but takes on a dome-like configuration, where the layers rise toward a central high point before dipping away in all directions. This dome structure would have initially elevated the central portion of the landscape above its surroundings. Once exposed to surface conditions, erosion began to act unevenly across this dome. The outermost layers, including the sandstone cap, provided initial protection. But over tens of millions of years, weathering processes gradually wore down this resistant layer. Eventually, erosion breached the sandstone, exposing the softer limestone and dolomite beneath. At that stage, the rate of erosion within the dome increased significantly as these carbonate rocks dissolved and were carried away by groundwater and surface flow. The result of this prolonged process is what geologists describe as a breached dome. Rather than remaining a raised feature, the dome becomes hollowed out from the inside as its core erodes more rapidly than its edges. The once elevated center transforms into a depression, while the remnants of the resistant outer layers persist as a surrounding rim. In Burke's Garden, this rim is expressed as the encircling mountains, while the interior has been lowered into the broad valley seen today. Closer examination of the valley floor reveals additional details that reinforce this interpretation. A subtle, elongated ridge runs through parts of the basin, representing an area where dolomite is more prominent. Because dolomite is slightly more resistant than limestone, it stands as a modest topographic high within the otherwise lower terrain. This internal variation aligns with the expected distribution of rock types within a folded and eroded dome structure. Another notable feature of the valley is the abundance of sinkholes, which punctuate the landscape in irregular patterns. These depressions form as limestone and dolomite dissolve beneath the surface, creating voids that eventually collapse. The presence of widespread sinkholes indicates active karst processes, a hallmark of carbonate terrains. Such processes would not be associated with an impact crater, where fractured and displaced rock would dominate, nor with a volcanic caldera, where igneous materials and volcanic deposits would be prevalent. The hydrology of Burke's Garden further supports its geological origin. Water within the basin collects and drains through a narrow gap in the surrounding ridge, where a stream has cut through the sandstone barrier. This outlet is not the result of a sudden rupture, but of gradual erosion exploiting a zone of structural weakness. Over time, the stream deepened its channel, allowing water to exit the enclosed basin while maintaining the overall integrity of the surrounding rim. The local climate within the valley exhibits measurable differences compared to nearby areas. Cold air, being denser, tends to settle into the basin, especially during clear nights. This leads to lower minimum temperatures and a higher likelihood of frost, even when surrounding ridges experience milder conditions. Seasonal transitions, particularly in spring and autumn, are often delayed within the valley, affecting agricultural cycles and vegetation patterns. These microclimatic effects are a direct consequence of the valley's enclosed topography and elevation profile. When assessing whether Burke's Garden could be the result of an impact event, several critical criteria must be considered. Impact craters typically display evidence of shock metamorphism, including features such as shatter cones, planar deformation structures in minerals, and the presence of high-pressure mineral phases. Additionally, the distribution of rock layers in an impact structure is usually chaotic, with significant displacement and mixing. In contrast, the rocks within Burke's Garden remain orderly and stratified, following predictable folding patterns without signs of sudden high-energy disruption. Similarly, volcanic origins would require the presence of igneous rocks, such as basalt or rhyolite, along with volcanic ash and other eruptive deposits. Calderas often show evidence of subsidence linked to magma chamber evacuation, as well as hydrothermal alteration zones. None of these indicators are present within the valley. Instead, the rock record is consistent with sedimentary deposition, followed by tectonic deformation and erosion. The regional context also plays an important role. Burke's Garden is situated within a broader landscape characterized by ridge and valley topography, a pattern formed by the folding and erosion of layered sedimentary rocks. While most of the region exhibits elongated ridges and valleys aligned with the direction of folding, Burke's Garden stands out due to its more circular or oval configuration. This difference can be attributed to localized variations in the intensity of deformation, which produced a dome rather than a simple linear fold. To the north and south of the valley, the rock layers transition back into more typical configurations, with less pronounced arching. This localized uplift explains why the valley is relatively isolated in its form, rather than part of a chain of similar basins. It represents a specific point where tectonic forces created a distinct structural feature that was later modified by erosion. Over geological timescales, the processes shaping Burke's Garden are ongoing. The surrounding ridges continue to weather and gradually lose elevation. Streams continue to transport sediment out of the basin, and karst processes continue to alter the subsurface. Given enough time, the defining rim may eventually be reduced to the point where the valley merges with adjacent lowlands, losing its current enclosed character. Yet even as these changes proceed, the fundamental relationship between rock type, structure, and erosion remains evident. The valley serves as a clear example of how relatively simple geological principles can combine to produce complex and visually striking landscapes. The interplay between resistant sandstone and more erodible carbonate rocks, the formation of a dome through tectonic folding, and the subsequent breaching and hollowing of that dome together account for the observed features without invoking extraordinary events. The persistence of alternative explanations, such as meteor impacts or volcanic activity, reflects the intuitive appeal of dramatic origins for unusual landforms. A nearly circular basin surrounded by higher ground naturally invites speculation about sudden, high-energy processes. However, the geological record within Burke's Garden does not support such scenarios. Instead, it points to a much longer and more gradual history, one that unfolds over hundreds of millions of years rather than moments of catastrophe. Even so, the questions raised by the valley's appearance continue to draw attention. Why does the rim remain so well defined despite ongoing erosion? How uniform was the original dome before it was breached? And to what extent do subsurface processes continue to reshape the valley from below, beyond what is visible at the surface? These uncertainties highlight that while the general mechanism of formation is well understood, the finer details of its evolution remain an area of continued study. The remaining uncertainties surrounding Burke's Garden do not stem from doubt about its origin, but from the finer-scale processes that continue to shape its present form. While the overall structure clearly reflects a breached dome formed through folding and long-term erosion, the timing, rate, and interaction of individual processes within the valley remain complex. Subtle variations in rock composition, groundwater flow, and surface drainage continue to influence how the landscape evolves, often in ways that are not immediately visible without careful measurement. One of the most significant ongoing processes within the valley is chemical weathering, particularly the dissolution of limestone. Rainwater, slightly acidic due to dissolved carbon dioxide in the atmosphere, infiltrates the soil and percolates into the underlying rock. Over time, this weak acid reacts with calcium carbonate, gradually dissolving it and enlarging fractures and voids. This process operates continuously, often at rates measured in fractions of a millimeter per year. Yet over thousands to millions of years, it produces substantial changes in the subsurface structure. As these voids expand, they can eventually destabilize the ground above them, leading to the formation of sinkholes. In Burke's Garden, sinkholes are not isolated anomalies, but a defining characteristic of the terrain. Some are shallow depressions only a few feet across, while others extend tens of feet or several meters. Both in width and depth, these features are dynamic, sometimes forming gradually and at other times appearing suddenly when the roof of an underground cavity collapses. The distribution of sinkholes is not random. It reflects the underlying pattern of fractures, bedding planes, and variations in rock composition. Areas dominated by pure limestone tend to develop more pronounced karst features, while zones containing higher proportions of dolomite may exhibit slightly different patterns due to its marginally greater resistance to dissolution. This internal heterogeneity adds another layer of complexity to the valley, reinforcing that its evolution is not uniform across its entire extent. Groundwater flow within the valley is closely tied to these karst processes. Rather than moving solely across the surface, water often travels through an intricate network of subsurface channels. These pathways can redirect flow in unexpected ways, sometimes capturing surface streams and diverting them underground. The result is a hydrological system that is partly hidden, with connections that may span significant distances beneath the visible landscape. Despite this complexity, the valley maintains a single primary outlet where water exits through the surrounding ridge. This outlet represents a balance point where erosion has been sufficient to breach the enclosing sandstone while still preserving the overall rim. The stream that occupies this gap continues to erode its channel incrementally, deepening and widening it over time. However, the resistance of the sandstone slows this process, ensuring that the enclosure remains largely intact over geological timescales. The shape of the valley also influences sediment transport. Material eroded from the surrounding slopes accumulates within the basin before being gradually carried out through the outlet. This creates a system where deposition and removal are continuously balanced. Fine sediments may settle across the valley floor, contributing to fertile soils, while coarser materials are more likely to remain near their source or be transported during periods of higher flow. Agricultural use of the valley has historically taken advantage of these conditions. The combination of nutrient-rich soils, relatively flat terrain, and a contained drainage system makes the area suitable for cultivation. However, the same features that support agriculture also introduce challenges. The presence of sinkholes can disrupt land use, and the colder microclimate can shorten growing seasons compared to nearby regions. Frost events may occur earlier in autumn and persist later into spring, affecting crop viability and timing. Temperature variations within the valley are closely linked to its topography. During calm, clear nights, cold air drains from the surrounding slopes and settles into the basin, a process known as cold air pooling. This can create temperature differences of several degrees compared to adjacent ridges, sometimes exceeding 5 degrees Celsius or about 9 degrees Fahrenheit. Over time, these repeated temperature inversions influence vegetation patterns, soil moisture, and even the types of species that can thrive within the enclosed environment. The symmetry of Burke's Garden remains one of its most striking attributes, yet this symmetry is not perfect. Detailed mapping reveals slight elongation along one axis, reflecting the orientation of the underlying structural deformation. The original dome was not a perfectly circular uplift, but rather an oval feature shaped by directional tectonic stresses. This elongation persists in the present day, subtly guiding drainage patterns, slope angles, and the distribution of internal features. Another important consideration is the thickness of the original rock layers. Variations in thickness influence how quickly different areas respond to erosion. Thicker sandstone layers can sustain higher ridges for longer periods, while thinner sections may be breached more rapidly. These differences contribute to the uneven evolution of the rim, even though it appears continuous when viewed from a distance. Over millions of years, the valley has likely undergone multiple phases of adjustment. Periods of increased rainfall would have accelerated erosion and dissolution, while drier intervals would have slowed these processes. Changes in vegetation cover, driven by climate shifts, would also have affected erosion rates by altering soil stability and water infiltration. Although these variations are difficult to reconstruct in precise detail, their cumulative effect is embedded in the current landscape. The broader Appalachian region provides additional context for understanding Burke's Garden. Similar, though often less pronounced, features exist elsewhere where domed structures have been partially eroded. However, few match the clarity and scale of this particular valley. Its preservation suggests a combination of factors, including the specific geometry of the dome, the resistance of the surrounding rocks, and the efficiency of drainage through its single outlet. Importantly, none of these processes require sudden or catastrophic events. The absence of disrupted strata, melted rock, or volcanic deposits remains consistent across all observations. Instead, the valley represents an accumulation of incremental changes, each one small in isolation but significant when integrated over vast spans of time. This gradualism is a defining characteristic of much of Earth's surface evolution, where the most dramatic forms often arise from the least dramatic mechanisms. The idea of a meteor impact or volcanic origin persists largely because of visual resemblance rather than geological evidence. Circular or enclosed forms naturally evoke associations with craters and calderas, especially when viewed without context. However, morphology alone is not sufficient to determine origin. In Burke's Garden, every measurable attribute, from rock composition to structural orientation, aligns with the model of a breached anticline dome shaped by differential erosion. As erosion continues, the future of the valley will depend on the balance between resistance and removal. The surrounding ridges will gradually diminish, though the rate at which this occurs will vary depending on local conditions. If the outlet deepens significantly, it could lower the base level of erosion within the valley, potentially accelerating the removal of internal sediments. Conversely, if the rim remains relatively stable, the valley may retain its enclosed character for millions of years to come. Subsurface processes will also play a critical role. Continued dissolution of carbonate rocks may expand underground voids, leading to further sinkhole development. These features could alter drainage patterns, redirect groundwater flow, and influence surface stability. In some cases, they may even create new pathways for water to exit the basin, subtly modifying its hydrological structure. Despite these ongoing changes, the fundamental explanation for Berchtesgaden's form remains consistent. It is not the product of a single event, but the outcome of interconnected processes operating across different scales of time and space. Folding created the initial structure, erosion breached and hollowed it, and chemical weathering continues to refine it. Each stage builds upon the previous one, producing a landscape that appears unusual but is fully explained by well-understood geological principles. The valley stands as a reminder that appearances can be misleading when divorced from underlying structure. A shape that suggests sudden impact or volcanic collapse is, in reality, the result of slow, persistent transformation. The evidence lies not in dramatic signs, but in the orderly arrangement of layers, the predictable distribution of rock types, and the consistent patterns of erosion observed throughout the region. As attention continues to focus on unusual landforms, Berchtesgaden remains a case where careful analysis replaces speculation with clarity. Its features, once interpreted through the lens of catastrophic events, now serve as a reference point for understanding how domed structures evolve under the influence of weathering and time. The valley does not conceal a violent origin, but instead reveals the power of gradual processes to shape the surface of the earth in ways that can rival the most dramatic scenarios. If you found this breakdown informative and engaging, take a moment to like, share, and subscribe, and tap that hype icon to help this video reach a wider audience.